Alright, what's up, Joe Gamers? Today we'll be using Cami. We're gonna be doing AP Physics FRQ. Today's first episode, we will be doing the question 2 lab, a portion of the FRQ. So, read the question, read the context first. Okay, and here's this. So, question A, which is right here, it is asking, based on these items right here, how can you find the K value of this spring? Now, there are many ways to get the spring constant. Actually, two. There is force equals negative kx, so and F, or energy, equals 1/2 kx squared. Okay, there. Now initially you're gonna think about using the force, because that's pretty simple. All you have to do is find the force, which would just be the weight of the cylinders, and divided by how much it displaces the thing, right? Well, if you look here, we don't have a ruler to see how much it's displaced, so the only thing we're given is a scale to measure the masses of these things, and we have a stopwatch to measure some time. Now, there is another equation that involves k, which is t, the period of a harmonic oscillating object that has a spring. It's like, what was it like this? Let me search it up. So, before we're even gonna start making a procedure, right here, we need an equation for k to solve for, right? And with these three equations, two of them cannot be one because they involve x, and we need an x, and a ruler to calculate x. So, whatever, yeah. We need a ruler to measure x. So yeah, we just use this equation, and if we solve for k, we get k equals 2 pi. Oh wait, no, my bad. 4 pi squared times m over t squared. So, notice that the only variables here we need to measure to solve for k is mass and time. So, we're given a stopwatch and a ruler, a stopwatch and a digital scale. So we can now solve for, we can solve for k. Let's write up a procedure. Now let's think about what we should do. Okay. So, to get points, we need to reduce error. We need to think of an experiment that will measure m and t at the same time, or not the same, but like in one whole experiment. And we're most likely going to have to do multiple repetitions of the whole entire lab, but with different weights. So, what should we do? Wait, need to turn this on. Now this is music I can teach in. So, the AP guidelines doesn't specifically say much about the general what you need to really say. It has 4 points, one being set the spring in harmonic motion, reduce experimental uncertainty, measure the weight of the mass, and time the period. That's the general point system. But to become a better scientist, and just to be sure that you do get your points, we're going to be a little bit more specific than those, and just marking off those check marks. So, we're going to design an experiment like if we're actually doing a writing steps on how to do it. So, first step is measure the, wait, it's going to be measure one of the, so measure the mass of one of the cylinders with the digital scale. I'm not supposed to chat. Cylinders. Measure and record. Oh, I spelled wrong still. Okay. Digital scale. Then hang the mass onto, cylinder onto the hook of the spring. Then, now, here's the thing. Notice the equation right here doesn't actually depend on how far you stretch the spring, right? So that means you are freely able to stretch the spring as much as you want. So you don't need to say stretch the spring 1 centimeter or whatever for each one, because realistically, it doesn't matter how far you stretch it. If it's in simple harmonic motion, it's going to have the same period, same whatever. Yeah, basically same period, because mass is going to stay consistent. So yeah. So same mass, same period. Doesn't matter how far you stretch it, because the equation never says that it's dependent on how far you stretch it. So, the next step is to say, then, stretch the spring, or pull the weight down. Pull the cylinder attached to the spring down a small distance, it's just a small distance. You don't need to specify how small. I mean, you could say 1 centimeter, but realistically, we don't know if it's just say small distance, right? And now, small distance to put the spring into simple harmonic motion. Hold on, this is getting way too tough. Alright. So, then pull, or I should rather say stretch the spring. Stretch the spring attached. Stretch the string down a small distance and release the cylinder to put the spring cylinder system in harmonic motion. There you go. So we just got measure. We got 2 points for measuring the mass and putting it into harmonic motion. 2 more points for measuring the period and measuring or decreasing experimental error. I'll write that one, the experimental error, later at the end. So we're gonna write in this part. Actually, no, we're gonna write both the how to reduce experimental error and record this period. So you're gonna say record the total time. Record the total time it takes for the spring to do one full oscillation, or actually not one full. It takes to do, let's say, arbitrary number like 20 oscillations. Whatever oscillations. Record the total time it takes the spring to do 20 oscillations. Now remember that oscillations in this period are not the same, but rather the average time it takes for one oscillation is the period. And to reduce experimental error, we're gonna do 20 oscillations to get the average period. So we're gonna say record the total time it takes to do for the spring to do 20 oscillations, and then we're gonna parentheses. Thus one oscillation being the spring being going from being fully stretched, or from being fully stretched, because the motion of the spring, if we pull it down a little bit, this is gonna be its max. Where my thing is at, there's gonna be where the max. It's gonna be the max distance. It's gonna stretch every oscillation. So it's gonna move like this and back, this and back. So we're gonna find the time it takes to go back to its small state and then back to its fully stretched state. So we're gonna write also being the spring fully stretched back to being fully stretched. Then divide the total time by 20 to get the period of one oscillation. Then you can say repeat steps. You probably want to say step 1, step 2. So I'm gonna say this is step 2 right here, but stop the spring and repeat steps 2 to, I don't know, this is like record. I think there's like 2 to 4. I think so. This is 1, 2, 3. Yeah. So like 2, 3, 4. Yeah. Okay. So 2 to 4. Let's say 5 times or something. It doesn't matter. I mean, I feel like you might be wasting time making it this specific, but you never know. Say 5 times. Repeat steps 2 to 4 5 times with the same mass or cylinder. Then repeat the whole experiment 3 times with changing masses. Then repeat the whole experiment with changing, but change the mass of this, or change the cylinder. Change the sum. So what we're basically doing is what I wrote for the last 2 to 3 lines, or reducing experimental error by repeating the experiment multiple times to get basically the average time it will take for just any mass to see how, as a trend, it'll stay consistent. And add up. No, you might. I don't want to yap that much, but you can just say that. Yeah, this is going way too far, but let me just finish it. Then add all the averages up and divide it by the amount. By the amount of times you've done it. I don't want to do that. I don't want to do the counting on how many times we're going to do. We probably did this like 15-ish times, 20 oscillations. So who knows? Divide by how many times you've done experiments. Basically, you're still going to probably get the same number, but it's actually, yeah. Just doing it multiple times with different masses will give you enough data to tell you if your other experiments were consistent. So now for vertical axis, so we're finding k, right? It says indicate which a linear graph whose slope can be used to determine the spring constant. Okay, so look back into the equation. Well, as we can see, the slope of the line, well, there's m on top and t squared on the bottom. Let me change that. So according to the AP guidelines, it's funny enough, it doesn't matter if the vertical axis and horizontal axis are m or t. It doesn't matter which order it is. But let's be real, we're not going to make a slope where we're going to inverse, because you can make the slope t squared over m and that still be an acceptable answer. But then in your explanation down here, you have to say you have to get the reciprocal, which you're just repeating. You're just doing extra steps. So just put mass and period squared, or period t squared as your thingy, right? And you could say put multiply 4 pi squared or whatever, but it doesn't matter. Both the AP says, the guideline says you don't have to put it, but you could put it. Let's just put it, make it easier on ourselves, and just not do it for the graph. Anyways, so now it says briefly describe how the slope of the graph can be analyzed to determine the constant k. Okay, for a brief explanation, it should be 1 or 2 sentences, and we can write, by plotting a graph of mass and period squared, we can determine the value of k by using its slope and relating it back to the equation of a mass and spring oscillate harmonic motion equation. And then we just write at the bottom t equals whatever, all the thing I wrote over here. And then you write k equals m over t, which is the slope. That's right. M over t squared times 4 pi squared. And then we just write that this is the slope. We just write like down here we write slope times 4 pi squared, whatever. That's all for that one. Alright. Okay. Last section of this one question. It's pretty long, but you know, it's still experimental is one of the largest sections of FRQ, so read this real quick, and yeah, alright. Okay, so here's the two graphs, sine, cosine graphs. They're both, if you notice, actually, that if you know a bit about calculus, you would know that this is a sine graph and this is a cosine graph, and we know that velocity is the derivative of the derivative of velocity is acceleration, right? And force is mass times acceleration, so it should still follow the derivative. Because since mass is a constant, this will follow a cosine graph because this is sine. Anyways, so this will be important to know when you do answer the last question of this. Alright, so first question. Given the data, calculate, so get the value of the change in kinetic energy from 0.5 to 2, and show your steps and substitution. So, Kf minus Ki, oh crap, that's bad, equals change in K, right? And notice that at 0.5, the value is 0.3, velocity is 0.3, and at 2 seconds, it's at 0. So we write 1/2 mv squared. Actually, we should just do 1/2, yeah, just do 1/2 mv squared minus whatever, blah blah blah. And then it's equal to 1/2 m vf squared minus vi squared. And if we plug in the numbers, we get 1/2 times 1/4. 1/4 coming from the mass of the thingy, by the way. Times 0.03 squared is 0.09. So that's like, I don't know, 1 over 9 over 100. Times minus, oh wait, oops. VS squared is 0, so this should be a negative actually. And what we'll get is the answer 800 over 9 joules. You gotta remember you have joules. And this value you're supposed to calculate, and I don't know if you can use your calculator or not on these. I think you can. And just plug it into your calculator, you get like negative 0.0125, I think, joules, and yeah. You might have to round this to 0.013, but whatever. Next one is estimate. Estimate the momentum, car, blah blah blah. Briefly explain. Alright, so 0.5 to 2.5, you can see the symmetry between the two, and you'll know that these two will cancel out roughly, as we're estimating that these two are roughly equal. The area is roughly equal here and here, but they're negative and positive. So you just type, you're not going to write an equation. You're right, using the briefly explain, you're not writing an equation. The change in momentum, oh by the way, change in momentum is F times T, that's why it's the area. The change in momentum is equal to force times time, the change in time, at T equals 0.5. I mean, the area between 0.5 and 2.5 are roughly equal, but opposite in direction. Therefore, they cancel out to 0. Therefore, the area cancels to 0, meaning the change in momentum is also 0. Like I say, the area under the graph is force times time, which is change in momentum. Between 0.5 and 0 roughly equal also, therefore cancels the meaning. There you go. I mean, it does say briefly, so you probably want to condense that to like 2 sentences. But yeah. Next one is, do the data from velocity time graph confirm what we got from CII, which is momentum is 0. And then you see from 0.5 to 2.5, you'll see that the momentum here, since they have the same mass and they have the same velocity, that means their momentum is the same at these 2 times. So therefore we can write briefly that momentum is velocity times mass. The mass stays the same, and the graph tells us that velocity at 0.5 and 2.5 t at time is the same at 0.3 meters per second. Therefore, if the velocity and mass are the same at 0.5, and 2.5, the momentum, the change in momentum is 0, which confirms what we got at CI. There you go. That's it.